Good morning to everyone. I am Precious Mahlambi. I'm a lecturer and also a director of studies in the chemistry department in Pietermaritzburg. Firstly, I would like to thank all of you for being part of this School of Chemistry and Physics online information session, which aims to help you learn about the study as well as the career options that we have in the School of Chemistry and Physics. I would also, on behalf of the school, I would like to welcome all of you. I would like to welcome our speakers for the day, which is Dr. Tishana Singh, a chemistry lecturer at the University of KwaZulu-Natal, Westfield campus. Dr. Nkosinathi Dlamini, who is a physics lecturer in the Pietermaritzburg campus, as well as Professor Thomas Conrad, who is the physics lecturer at Westfield campus. He's also the academic leader of physics. So I believe at the end of this session, we will all be able to understand better what the School of Chemistry and Physics offer, and also why you should do chemistry and physics. Okay, please let's keep our mics off and also the videos just to save data. If you have any questions, you can type your questions on chat. However, we're also going to have a live question and answer session at the end of all the speakers. Okay, as the School of Chemistry and Physics, we do have two sites. One is at Westfield campus and the other one at Pietermaritzburg campus. Both of these campuses, they offer undergraduates up to PhD levels. Within the school, we have about 60 academic staff, which are responsible for teaching as well as for research supervision. We have 68 technical staff members, which are responsible for ensuring that our undergraduates' practicals run smoothly. We also have admin staff responsible for the administration of the school. We have about 2,000 undergraduates as well as 600 graduate students within the school in both campuses, of which most of them are mainly from KwaZulu-Natal province, but we also have a number of students outside the province, as well as outside Africa or outside South Africa. As a school, we also involved in research, where we have one of the state-of-art research equipments, like this one shown in the picture here, which is called the plasma laser deposition, which is used mainly to make thin films. And these thin films, they have variety of applications, and some of them includes, they can be used in our homes, as well as in our cars, and the windows, to help and reduce the reflection of sun, especially the harmful sun rays. As a school, we are also involved in collaboration, research collaboration, locally as well as internationally, which is very important to broaden our research skills as well as knowledge. Locally, we do have other countries that we work with, like Kenya, African countries like Kenya, as well as outside Africa, which include Korea, China, USA, as well as Germany. So after having introduced mainly about our school, now I would like to give the stage to Tishana Singh, who is going to tell us more about what the School of Chemistry offer. And then she's gonna explain to us why should we go and do chemistry in KwaZulu-Natal. Tishana, the stage is yours.
Okay, thank you, Dr. Mahlambi. Okay, can you see my screen?
Yes.
Okay, great. Okay, good morning, everybody. As Dr. Mashlambi introduced me, my name is Tishana Singh. I'm a lecturer in the School of Chemistry and Physics. I'm based at the Westville campus, but I actually lecture at Howard College, and I'll explain to you why I am at Howard College. Okay, my slide is not moving. That's a bit strange. It's not moving.
Shana, try maybe just to do it with the cursor buttons. You know, there's left, right, up, down, and
Yeah,
if that doesn't work, try to click on the mouse pad.
It worked when I tried it.
Yeah,
Okay.
this is always a show effect.
Yeah.
Try it again. Yeah.
Ah, there we go. Now it works. Okay, so I'm assuming I'm talking to mainly people from school who are probably grades 9, 10, 11, maybe 12, or whatever, or maybe even lower grades. So you probably have a lot of pressurizing questions at the moment. Like what do I study after I finished school? What do I want to do? What do I like doing? What do I want as a career? What's my passion in life? Where do I like to work? Do I like to work in the lab? Do I like to work in the office? Do I like to solve problems? So you have a whole lot of questions in your head on exactly what you want to do or what you would like to do. So let's just say one of the answers you have is that you do like science and you would like to do something in science. So the next thing is, okay, fine, I would then like to do a BSc in chemistry at UKZN. I'm assuming you are all here in KZN. So the best choice is your university of choice, which is the University of KwaZulu-Natal. Now we offer various 3-year degrees, the BSc degrees. And as you can see, I've listed them there. There's a whole lot. There's chemistry with applied chemistry, with environmental science, biochemistry. There's a whole list of it. Now, all of these degrees require that you must have fairly good marks in maths and physics, right? That is one of the requirements for a BSc degree. So now I will tell you a little bit about exactly what the other requirements are. And in order to do that, I'm just going to guide you through to the website, right? So if you go to the university website, right, www.ukzn.ac.za, and I've marked the block there, colleges. If you click on colleges, a red drop-down menu box will open up. Click on the School of Chemistry and Physics. So if you click on that, it will take you onto the next page. This is our new page. It was just launched, I think, last month. And the next page has sort of like a moving banner with different aspects in the school. But on the page, you will see two sort of headings near the head of school, Prof. Ross Robinson, Chemistry and Physics. So in order to find out exactly what chemistry is about, if you click on chemistry, it will take you to the next page. And this is where you will find all the information that I'm also going to give you, right? So there's videos, there's a lot of PDFs which you can download and read. but I'm presenting just a few of the most critical information from those PDFs, and I will direct you to exactly which ones they are and where you can find the information. The other thing you will find on this page when you click on chemistry is the academic leaders for the different clusters. Now, we are referred to as clusters because we have chemistry and physics on 2 campuses, right? So we operate at Westville as well as Pietermaritzburg. And we have an academic leader for chemistry and physics on both of those campuses, right? And their details can be found on this page as well. Right, so one of the downloadable PDFs that you will find on that page is the Undergraduate Prospectus. And if you go through it, I think it's on page 14 or 15, you will find the entrance requirements for the BSc degree, right? So this is for the BSc degree across the campuses for chemistry as well as engineering. This is for the faculty, right? And they also, what is also given, right? It's very nicely laid out with all the information that you need, right? The National Senior Certificate for degree studies. They also give you information if you do get a National Senior Certificate for diploma studies, what exactly you qualify to study. Then on another page, you will find the calculation, the APS calculation for the degree. Now, APS stands for Academic Performance Score, and it is the scoring we used at the university, the point system. As you can see on the table on the right-hand side, I've put down the point system that is used at the university, which is the table on the top. And the second table is an example of how the point system is applied, right? So this is taking someone's National Senior Certificate degree results and putting in the APS scoring, the point system, in order to tell you what points you have and whether you qualify to do the BSc degree or not. Now, please note, in one of the downloadable PDFs, you will see that the point system ranges from 28 to 45. Now, 28, now please note, is the minimum, right? So we usually take the higher. The higher the points, better your chance of getting in, right? So don't aim for the minimum. Right, so what is reflected in the PDFs online is the minimum requirements. Okay, so you have made up your mind now that you want to do a BSc degree in chemistry. And as I said, there are 2 things. You can have a chemistry major or you can have an applied chemistry major. So these blocks that I've got here, let me just bring them. So I've put down as a chemistry major and applied chemistry major. But as you will see, for the first year, we call it level 1. The first year, the BSc students do exactly the same thing, right? So if you think you're coming in year 1 and I am going to do applied chemistry, no. Applied chemistry is based on a selection process, right? So after year 1, you then need to apply to do applied chemistry and you undergo a selection process. So applied, you can only get into applied chemistry when you choose your majors in your second year, right? And that is based on merit. It is based on your first year results. You do not automatically go in to do applied chemistry. The selection criteria is quite stringent and quite strict. So you don't automatically go in. So as I said, everybody in the first year does the same courses, or we refer to it as modules, right? So in semester 1, you will do level 1 chemistry. First year, we refer to it as first year chemistry, Chem 110, Chem 120, semester 1 and semester 2. You do first level maths as well in both semesters, as well as physics in both semesters. And then you have the choice. So even in year 1, we give you the choice of choosing something that you would like to do. But even in those electives that you choose, we caution students to do something that will help them once they choose their majors, right? And if you look at the handbook, now for this information, you actually need to download the prospectus, right? The prospectus is also online, and it will give you what electives you can choose in your first year. Now, let's just say you've completed your first year, and you've also been selected to do applied chemistry. So now what do you do in applied chemistry, right? Now, just as a comparison, if you had chosen, say, for example, to do microbiology, right? So if you're doing microbiology, you will also do these chemistry courses. These 3 chemistry courses here, 210, 220, and 230, refer to organic chemistry, inorganic chemistry, and physical chemistry. Now, when you do chemistry 1, we briefly introduce you to all these levels of chemistry. We give you some background to each one. But when you come into second year, we now need to teach you a little bit more on these different topics. So then we break them down into their various topics. But if you have been selected to go into the applied chemistry major route, that is where we introduce the applied chemistry modules, right? So now your major, if you were doing microbiology, will be something in micro. But if you are going the applied chemistry route, the applied chemistry major, we introduce semester 1, your first applied chemistry module, which is Chem 221. I think it's environmental chemistry, right? And then in semester 2, you do physical chemistry, as well as chemistry and industry and chemistry analysis. Now, what exactly do you do in these courses? Now, remember, applied chemistry, and I'm going to talk a little bit more. Let me just finish. In level 3, you do, again, the advanced organic, inorganic, and physical chemistry, as well as chemistry and industry, material science, and chemical analysis. But the module that actually puts everything together in semester 2 of your third year is APCH 342, which is the integrated project. Now, the integrated project, our third year students get the opportunity to do a project that now encompasses everything that you have learned in the past 2.5 years, right? All the various chemistries that you have done, all the pracs that you have done, all the equipment that you have worked with, right? So in second year, we start introducing you to equipment in the labs, right? So we have some very high-tech equipment that does very analysis that you probably only hear about and see on TV. So we've got high-performance liquid chromatographs, we've got gas chromatographs, we've got the NMR, nuclear magnetic resonance, we've got the ICP, we've got mass spectroscopy. So we've got a lot of high-tech equipment. And in the second year, we start introducing you to it, right? So by third year, when you do Chem 312 and 332, you should be good enough to actually operate these instruments, carry out analysis, as well as come up with the method of analysis, right? So part of your training is to develop methods. How do we go about doing certain analysis? And all of that comes together when you do the integrated project, right? So we give you a chance now to show us that you have learned your chemistry and you can apply it. Because when you go to industry, because ultimately the goal is to go into industry, whatever industry it is, I will talk about that now as well, that you must be able to apply your chemistry knowledge. Okay, so enough of the courses that you're going to do. So what exactly do we teach you in all those courses? Now, chemistry, applied chemistry in particular, is applicable to anything around you, right? So we're talking about pesticides, we're talking about foods, we're talking about environment, in the food industry, the medical environment, the cosmetics, all of your household detergents, we're talking about electronics, transport, manufacturing, car manufacturing, even space. So everything is covered, right? So in environmental chemistry, you will learn about pesticides, about soil analysis, how to do soil analysis, what is required in developing a method, the equipment used, more importantly, what are you looking for in soils? Are you looking for organic contaminants? Are you looking for metal contaminants? In the food industry, we also look at the range of things. Now, food also has to maybe have certain qualities, your color of foods. Like, say, for example, I've worked in the sugar industry, so I will talk about sugar. Sugar has to be a certain color. Sugar has to have a certain pH. The grain size of your sugar, it has to be a certain grain size. So all those kinds of things. In the cosmetic industry as well, the formulations, your lotions, your creams has to be of a certain consistency. Your soaps have to have a certain amount of sodium lauryl sulfate in it to give it that foaminess. Your shampoos, those sort of things. In your cleaning as well. So detergents are made up of ammonia, sodium hypochlorite, sodium hydrogen chloride is also used for cleaning. So all of those formulations have to meet certain specifications. So how do we make sure that they meet those specifications? More importantly, how do we formulate them in order that they all stay together? Because you don't want, for example, if you're putting in your sodium lauryl sulfate into a soap, that it must separate. So there's a lot of chemistry that goes into making sure that everything stays together. In all the electronics, there's some sort of chemistry involved. You've got precious metals, you've got silicon, you've got copper, gold. There's a whole range of things. In the car industry, you're looking at electroplating. Now, this is where your electrochemistry comes into effect. The paints, the oils, the lubricants, everything that goes into cars. It has to meet certain specifications. So there is a range of things that with an applied chemistry major that you can do, right? So there's also the medical field as well. So I come from a background of industrial experience. In the manufacturing experience, my manufacturing experience comes from working in a sugar mill, and I've also worked in the medical environment in pathology, right? So we're looking at analyzing blood and tissue and all those kinds of things. So there's applications in everything. Right, so the other thing that you will find on that site is a poster that gives you a list of all the careers, right? The careers, as well as the degrees that you could do if you want to do certain things. Now, I would advise you to read brief descriptions that are given for each one, as well as the kind of the areas of employment, because ultimately what you want to do is actually go out and work. Now, of all the careers that are listed there, the forensic scientist, the green chemist, the materials scientist, as well as the medicinal, the physical chemist, the theoretical chemist. There is a huge scope, and there are lots of intertwined areas. So for example, if you are a forensic scientist, we don't really have many forensic analysts in this country. It's usually with the South African police, but they are really backlogged with a lot of work. There is also combined with a material science as well as a physical chemist or a medicinal chemist. So it's the other thing I'd like to also tell you. Someone's got their mic. You would also have to know a lot about metals. If you medicinal chemistry. If you're searching for drugs in someone's blood, or analyzing a blood splatter or whatever it is. But just on note, a lot of people are very taken by forensic scientists. You cannot just be a forensic scientist with your degree, right? A lot of postgraduate study is required to further develop your skills to be a forensic scientist, right? Because as I said, all the equipment that I mentioned, if you are a forensic scientist, all these analytical equipment that I mentioned, you need to be able to analyze results from those that are generated by that equipment. Okay, and then there is a physical chemist, as I said, and a theoretical chemist. So the theoretical chemist is a little bit different from the norm. So it's a computational chemist, mathematical chemist, and chemical informations. So that now is more looking with working with computer programs. And but you also need to have a very good background of wet chemistry, right? So that was the last addition to that. Right, so these are just a few pictures that I've put in of our labs. Now, and also, as Dr. Mashlambi mentioned, we have many labs. I don't want to give you the number of labs that we have, but we have many labs and we have big labs. So each person gets to do their own track. There is no such thing as working in groups or pairs. So when you are a first-year student, you would go to the lab and you would be assigned a space in the lab and you will be doing your own track. So you would be assigned a locker with glassware and equipment, and you would do your own tracks. The other thing in our labs, we also have our postgrad students helping us. So most of the time as a first-year student, first-year students are a little bit afraid or scared to talk to the lecturers. So we have postgrad students in the lab helping these students. So you get a chance to work with our senior students. These are students who are doing masters and PhD in applied chemistry. They are more than qualified to help you answer all your questions in the lab. And as Prof. Conrad mentioned before we started, if you were in the already on Zoom, you would have heard that the postgrads are also going out into the community teaching students as well. So yeah, we have really good labs at Westville and at Howard. Oh yes, so I was going to say that the reason why I am at Howard is if you are thinking that after listening to me that applied science is not for you, you would rather maybe go and do engineering. You're not going to get away from chemistry. Engineers also do chemistry. So that is the reason why I am at Howard College, is because I teach chemistry to the engineers. So yes, if you're thinking of doing engineering, you have to do chemistry as well. Right, so we also have a few research areas, and I'm not going to talk about the research because Prof. Conrad will talk to you more about research and what it details. And that's all from me. So thank you very much for listening. And I hope I have given you sufficient information on chemistry and why we do chemistry. Thank you very much.
Thank you, Dr. Tishana. Yes, by now we do know why we should do chemistry at UKZN. Now I'm going to hand over to Dr. Nkosinathi Dlamini, who is going to tell us more about what the physics department offer and why we should do physics at UKZN. Doctor, over to you.
Hi, thank you. Good morning, everyone. My name has been introduced as Dr. Nkosinathi Dlamini. I'm a lecturer in the physics department at UKZN, based on the Pietermaritzburg campus, as well as being the first year physics coordinator on that campus. And I've been invited here today to speak to you a bit about the physics discipline here at UKZN, with a focus on what goes on in our undergraduate program. Prof. Conrad will discuss more about the postgraduate program and the research in the school. So I thought a good place to start would be with the question of, well, what is physics as a starting point, right? And well, I suppose physics means different things to different people. And the word physics itself comes from, I think it's two Greek words, physis, which means nature, and physica, which is the knowledge of nature. And it is really about studying nature and how it works. Now, some people describe it as the science of matter, energy, space, and time. What one could say is that physicists study the interactions that exist between matter and energy. And this might lead you to the question of, well, what kind of things are these? And what you'll typically study in your physics courses is things like energy, force, light, and movement, right? You'll look at the way that matter moves through space and time, and how things like energy and force affect that particular movement. And what you're really trying to discover is exactly how the universe behaves, or how some system of interest, some subsystem of interest behaves. So during the course of your studies, you'll be learning about the fundamental laws of the universe, things like why don't we float up into the sky, which you should already know, hopefully by this time, but you look at it in depth. Why do objects like your hands look different when you place them underwater and you're looking at them? Or if you're underwater and you're looking up through the surface, why do things look different and slightly shifted? And if you look up physics, you'll find that it's in fact one of the oldest academic disciplines around. And I think through the history of man, nearly every civilization has had some form of physics, right? It's essentially the way that we understand the world from a scientific point of view, right? Not only that, it also forms the foundations and is connected to all the other branches of science and engineering, right? You'll find it useful in everyday life, and as well as in many professions such as chemistry, life sciences, agriculture, engineering, the medicinal field, etc. These all rely on a physics background. And now that we've covered sort of this broad idea of what physics is, well, what I want to touch on next is, what do we study in physics? So here on the slide, you currently have this symbol, which is known as the Ouroboros, this ancient symbol depicting a snake eating its own tail. And well, I put it there because it was essentially adopted as the symbol for alchemy. And alchemy, for those of you who don't know, is an ancient branch of natural philosophy and a precursor to physics as we know it today. And one of the most famous alchemists in history was Sir Isaac Newton, who happens to also be one of the most well-known physicists. I believe even people who haven't studied a physics course can tell you at least one of his 3 famous laws, right? Now, shown on the Ouroboros here are the range of objects and the range of sizes that are governed by the laws of physics and that you will study as a physicist, right? Physics will give us this opportunity, and it allows us to probe the extreme parts of the cosmos, right? From very large to very small. You can go all the way from the very building blocks of the universe, say on this end here, in the form of subatomic particles, very, very small size. So these subatomic particles, things like the behavior of quarks and gluons and leptons, right? And these combine to form atoms, and you study this through cellular level objects on, say, living organisms, planetary size objects, through to celestial bodies like galaxies, like solar systems and galaxies. And all of these objects are governed by the laws of physics. And what you'll be doing as a physicist is, well, you'll be probing key questions, and I suppose the key questions depend on which area you're probing about nature, and you're going to be trying to find a deeper understanding of why things happen the way they do, right? And as you can see here, the range of topics or the range of investigations that you can perform is quite vast. So here at UKZN, we essentially offer two different programs in physics, right? We currently offer a physics major that's offered on both the Pietermaritzburg and Westville campuses, in addition to the newly introduced applied physics major, which is offered on the Westville campus. Now, to get into either of these programs, the physics major or the applied physics, you need a minimum of 30 points. I know for the BSc, I think it's 28, but to get into the physics program, you require a minimum of 30 points, excluding life orientation, as well as a minimum of 5 points for your mathematics. So if you're planning on becoming a physicist, please make sure that you practice your mathematics, right? The other information in terms of the other subjects and the other points that you require, you can find those on the prospectus. I did post a link in the chat, but I will post a link again after this, right? And basically, if you have any questions, if you go through the prospectus and you still have questions with regards to the entry requirements and what you need to come in, they are both 3-year degrees. This is my email address. So you can feel free to shoot me an email. I will try my best to assist you if I can. Sorry, someone has their microphone. Yeah, sorry. Sorry about that. So yeah, I'll try my best to either answer your questions. If I can't answer your questions about getting into either programs, I will put you in touch with somebody who can. Now, in terms of the two programs, if you look at the course outline, you'll notice that both programs essentially offer the same, what I would call foundational courses. And these are the courses that are highlighted in yellow on the physics major, but you'll find them also across on the applied physics side, right? And so they apply to both programs. And in these courses, the idea is that you gain a broad understanding of the fundamental theories. So you get this nice, broad knowledge base. And you need this broad knowledge base to try and make sense of the world around us on a deeper level, to try and probe further, right? Here, you're going to delve into topics. You'll look at things like classical mechanics. I think starting off in Phys 113, you start off essentially from where you left off in grade 12, but you go deeper and you go into the more technical details. You look at classical mechanics, you'll look at thermodynamics, electromagnetism, optics, all the way up through to quantum mechanics in these courses here, which also reflected on the applied physics side. And I've also highlighted the necessary maths courses. The maths is quite important because mathematics is the language that physicists use. On the applied physics curriculum, there are also these other physics courses that are included, which I've highlighted in light blue. And these focus on the application, more on the application side of some of the theories that you cover in the fundamental courses. So you'll see that in the second year, they've got this Phys 231 and Phys 242. And in those courses, you go through an in-depth review of the mathematical methods that physicists tend to need. So it's maths, but focused on the needs of physicists, as well as an introduction to machine learning, electronics, and energy systems. Whereas in the third year, in Phys 343 and Phys 345, you cover in greater details topics such as machine learning and machine learning for physicists or applied to physics problems. You cover topics like instrumentation, where you look at how to calibrate lab instrumentation, deal with lab instrumentation, etc. There's also a very nice course on renewable energy and fiber communication, These topics in blue here, I would say, are very nice because they are essentially at the forefront of what has been termed the fourth industrial revolution, and they align themselves quite well with the way the country and the world as a whole is moving. Now, I thought it would also be nice to see how some of the fundamental topics in the physics major translates to everyday use. And to illustrate this, I just picked the example of a car. So this is the car I'll be using, and it's the Nissan GT-R4. Now, when you begin your journey into physics, one of the first topics you start off with is classical mechanics. That's essentially where it starts, your journey starts. And what classical mechanics is just the study of forces acting on bodies, whether the bodies are at rest or in motion. So in this particular slide, I suppose, in this example on the slide, mechanics could be the spinning motion of the wheels. And in particular, you could be looking at things like the contact that exists between the tires and the ground and the frictional force that is generated there, which in turn determines the amount of traction you get, whether you're trying to, pull off, accelerate, or stop. You also spend time looking at the topics of waves. Now, in waves, what you study there is essentially vibrational motion, if you want to sum it up briefly. And with the car example, that would include things like looking at how your shock absorbers work, where the sound system speakers should be placed within the cabin to ensure maximum sound clarity and quality, as well as things like how to insulate the sound from your car, because if you're inside the car, you don't want people outside hearing what you're saying inside the vehicle, and vice versa, as well as you also don't want to be exposed to too much of things like the engine noise. In thermodynamics, what we do there is we study the relationship that exists between heat and other forms of energy, and that tends to lead us to things like how to design an efficient engine in this car example, as well as how to use things like the waste heat that's generated from the exhaust and when you apply the brakes. And if you are a fan of Formula One racing, you can just think of the Kerr system that they use there, which essentially recovers waste heat and uses it to charge up the vehicle batteries. In electromagnetism, which is one of my favorite topics, we study the properties of electric charges, magnetism, and the relationship that exists between them. So for this car example, it would be things like the car battery, the starter lights, the alternator, and how all the circuitry is put together. Optics is the study of light, and there's another topic that is quite interesting. In this car example, you'd be looking at things like the optimal positioning of the headlights within the casings, whether you use the LEDs or the halogen headlights, the positioning of the mirrors, the curvature of the mirrors and the windscreens, and how those all affect your vision as you drive. And the final topic that's sort of foundational that you do within your first 2 years is what's known as modern physics, which I haven't quite depicted on the slide. And modern physics is a lot of fun, right? It's a study of what I like to term, or what I usually term, the weird stuff in inverted commas. Not that it's weird, but I call it that because as you start venture into your journey into modern physics, you start to encounter results which don't quite conform to your intuition and what you would expect. And things seem very, very strange, especially at the start. So an example of a byproduct of modern physics in terms of this car example, I would say would probably be something like the ECU chip, which controls all the electronics in the car and is essentially the brain that controls all the electronics and controls of these modern day cars, right? Now, the skills that I've mentioned here are by no means the only skills that you'll pick up during the course of your studies with us here in physics. And in fact, what you'll find if you go through the prospectus or the course or the college handbook is that most scientific courses will either require you or strongly recommend that you take at least one physics module during the course of your undergraduate studies. And this is because aside from the actual physics theory, you learn a lot of soft skills in your time in physics, right? Because as you progress through a typical physics module, some of the skills that you'll pick up. I think I've highlighted just 4 on the slide here. We've got problem solving, where you learn how to really define a specific problem, break it down if it's a large problem into a set of smaller steps, analyze those steps, identify possible solutions, select the best solution, formulate a plan of action, implement the plan of action, and get some sort of feedback and go through the steps again if you don't have the optimal solution. You also require, the typical physics course also requires a lot of the analytical and critical thinking, and that usually involves taking outside knowledge, so maybe something that you learned in mathematics, and taking that into account when presented with a particular problem. Maybe there's some theorem that you did in one of your maths courses that simplifies the problem greatly, right? And here you really begin to be able to take complex problems apart and break them down into manageable components and incorporate techniques and methods from different fields to find a workable solution. One of my favorite things about being a physicist and studying physics during my time as undergraduate was the autonomy and independence that it afforded you, because this really allows you to grow as a scientist in general, as well as a person, because what you'll find is that in the majority of your physics courses, your lecturers will encourage you to, either through hints or suggestions, to interrogate the theories that they put before you, right? None of your lecturers are going to be happy if you simply regurgitate what they put in front of you. They really try and encourage you to interrogate everything and try to reach your own conclusions. So then you are encouraged to read around the topic, and there's a certain level of responsibility and independence that is quite useful to attain, that you get through at least going through one of these courses. And the last one is, I would say, communication, because this is another key skill, because especially in these days, no one really works in isolation anymore. And physics is one of the sciences where you need to be very clear. Sorry about that, wrong slide. Where you need to be very clear in terms of what you're saying. You need to be clear, you need to be ambiguous, unambiguous, and it forces you to learn how to be clear and precise in your communication. Now, you'll come across this because some of the work you'll do in groups. So for example, if you're in the lab, in one of our physics labs, you typically work in groups of 2, and you need to be able to communicate with your partner. Now, these skills are nice to acquire because they are transferable to many other disciplines. And because of this, you'll often find physicists working in a vast array of careers. Now, usually when you talk about careers in physics, people usually think of either academics working in academia, researchers stuck in a research lab somewhere, or somebody teaching maybe in high school. So I thought it would be nice to try and highlight some careers in physics that aren't usually associated with physicists. So the first career does get associated with physics quite a lot, but it would be in the space field, right? There's quite a large number of career opportunities in space for physicists, because what you'll find is if you go to any country that has a space program, there are physicists involved in every one of those space programs at various levels and degrees. Maybe you don't want to become an astronaut or you don't want to become involved strictly with a space program. That's still okay, because quite a lot of physicists apply their skills, for example, as astronomers or cosmologists, and they study stars and galaxies and other celestial objects from the ground, right? And UKZN currently has a fantastic research collaboration with the South African National Space Agency, SANSA, as well as the Square Kilometer Array projects, as well as hosting one of the NASP nodes on the Westville campus. So other jobs would be, for example, in the stock market, where you often end up having physicists who use advanced mathematics to solve problems. So most of those mathematical methods that you start to learn in second year, it turns out can be applied quite well to making predictions on the stock market. So things like Brownian motion, for example. And it turns out that currently physicists are in fairly high demand at financial companies who are in search of these mathematical skills. Another one would be in medicine, So physics has contributed in countless ways in the medicinal field. Start off with, say, quantum mechanics, which has led to the understanding of chemical reactions on which drugs are based. We've got the CT scan, which is the machine that's depicted here, which allows you to image the inside of a patient's body without having to cut into the body. And this was in fact invented by a South African physicist, Alan McCormick, as well as other medical machines and techniques which owe their existence to physics. So for example, X-rays, radiation therapy, ultrasound, pacemakers, MRIs, and the list goes on. But stop there with the medicinal. In terms of the stock market, you again often use the advanced mathematics, sorry, not the stock market, in terms of investment banks, which I've listed a few investment banks here, the first 12 or so that I could find. They often also employ physicists. Again, it's the mathematical skills that they're after in regards to the mathematical modeling that you learn as a physicist. Now, this list is quite exhaustive, and these are just a few examples of where physicists end up working. There's a very nice poster on the school's website that lists the various careers as well as the study paths to get into those careers for physicists. I will post that link in the chat once I am done here. Right? But the take-home point that I wanted to make with this particular slide is that there is, if you want to study physics, there is more out there than simply ending up in academia or working in a research lab, unless you want to end up in academia or you want to end up working in a research lab, which is also fantastic. So I think I want to end here. So I would like to thank you for your time and coming to this information session this morning. I hope that you have found it useful. If you have any questions, please feel free to ask using the chat facility. It does get a little jumbled up, but we will try and assist you as best we can. As I said earlier, you are free to send me an email. And if I can help you, I will do so. Otherwise, I'll point you to the person who can. So I'm going to stop here and I'm going to hand you back to Dr. Mahlambi, and thank you for your time.
Thank you, Dr. Nkosinathi, for such a valuable information on why should we do physics. Now I'm going to hand over to our next speaker, which is Professor Conrad, who's going to tell us more about research. Why should we study up to postgraduate level? Why should we do research? Which problems can we be able to solve with the research that is being done at UKZN? Professor Conrad, over to you.
Thank you, Dr. Mahlambi. I would like to say hello and show you some examples of our research. Okay, this is the end of the talk. So you see already what I will lead you through. And it's about the research in the School of Chemistry and Physics. And our research is very versatile. And I want to show you three things. The one is that we are one of the leading research institutions in the country for chemistry and physics. And in some cases, we do world-leading research. The second thing is that our research is also very applied and very relevant to the industries. And the third thing is that I think our research is very exciting. Okay, so by the way, here on the left-hand side, you see a picture of a solar storm. So there is, due to changes in the magnetic field of the sun, there can be large explosions in the atmosphere of the sun. And then also the magnetic field of the Earth, which is usually kind of protecting us from charged particles flying onto the Earth, because the magnetic field lines here are kind of repelled. So you must imagine it is like it is like if you have two bar magnets, and the bar magnets are kind of, if the same poles point towards each other, then the magnetic field lines are repelled. You know, you see here, like they are repelled, the blue lines here. But if the field lines, if the poles are opposite, so I have a north pole, let's say at the sun, and a south pole at the Earth, then the field lines connect, and then particles, charged particles, can circle around the field lines and hit the Earth from the sun. So there are these explosions, and there's lots of plasma, lots of charged particles, and they fly towards the Earth. And then that can do a lot of damage to electric grids, and transformers can be damaged. So 30 years ago, there was a large such an event that blew out the electric grid of Canada for quite a while. And we call this the space weather, and it's very important to do research on it, and in order to predict events that happen on the sun. And we have here one of our research centers, I think in KwaZulu-Natal has mentioned it, is the NASP node. We do the space weather there together with SANSA. SANSA is the NASA of South Africa, if you want, South African Space Agency, and we predict these things. And that is one of our researches that is going on. My next point is I would like to introduce you to cosmology. Cosmology is the study of the evolution of the universe. And in order to give you a small glimpse, I would like to go with you through the first second in the life of the universe. According to the Big Bang theory, the universe started in a singularity. And the Big Bang at first was not so big. It was actually, the universe was in a very, very tiny spot, much smaller than the nucleus of an atom. And after a split second, it went into a phase transition, and it expanded to nearly the size it has today. That's an expansion factor, if you want to compare the size it had before to the size afterwards, of 78 orders of magnitudes. That means you have to multiply, let's say, the diameter, the length scale, by a 1 with 78 zeros behind there to get the size it had afterwards. So that was a large expansion. And in order to give you an understanding of what a phase transition is, I would like to refer to the example of freezing water. So if you cool water down to 0 degrees, it starts to freeze, you get ice. Of course, in the process, you expand as well. And the freezing process needs a crystallization seed. That means it needs to start somewhere, and that is usually an impurity in the water. And if you take very, very pure water, then you can cool it down below 0 degrees, let's say maybe even to -14 degrees. And then this is super cooled water, and it will not freeze. But if you have such super cooled water in a cylinder in your lab, and someone comes in and just coughs, then the disturbance due to the sound wave might induce a small crystallization seed, a small impurity at your cylinder, at the surface of your cylinder, and then the crystallization process starts, and the whole water will crystallize in one moment, and the whole cylinder will explode, right? And that is another example of a phase transition that can be a very violent event. And here in this case, the phase transition was not matter that expanded, it was space itself that expanded. And in the beginning, there was just a single force, and due to the expansion, the temperature dropped drastically, and the force split into the 4 forces that we know. There's gravity that holds the solar systems together. Then we have electromagnetism that holds the atoms together. Then we have the strong force that holds the nuclei together. And we have the weak force that is responsible for the decay of atomic nuclei. And physics is to a large degree about understanding the four forces and finding applications everywhere. Like, we mentioned energy systems. How do we produce energy? How do we transport it? How do we build devices? And basically every technology, modern technology that we have has some touching points to physics. So there is lots to do, and we need your help to develop this further. Let me come to another example, or maybe let me say that what we do in cosmology here at our institute is we look at the afterglow of the Big Bang. So there is still a temperature of 3 degrees left from this big explosion, if you want. And we analyze the data in order to find out what really happened at the Big Bang. So let me go to this example here of a world first in chemistry. Namely, this is about small nanospheres, so-called quantum dots. So you can think of a chemical compound that is enclosed in a small nanosphere. You see here, like it says 3.45. The units is nanometer. So this could be something like 1 nanometer is 10 atoms, maybe. So 30 atoms or 34 atoms, and belonging to this compound. And if you enclose charges in, so there are electrons inside, and if you enclose them into very small spheres, then something happens that is very fascinating and was only discovered, let's say, 120 years back. Namely, the energy of these electrons is quantized. It means it comes in small packets. Quantum is a name for a small packet. And that gives you fantastic optical properties. So you can build lasers with this. You can do solar cells. You can build LEDs. You can have electronically single electron transistors. And we use it here. Our colleagues in chemistry use it to produce plastics that are more eco-friendly. You might know that plastics enter the food chain because they somehow, a lot of plastic ends in the sea, and then it decays, and you have these small fibers, plastic fibers, and they are eaten first by plankton, then by fish. It enters the food chain, and it causes lots of damage also to humans. So here we have some plastics that do not decay in this way, and they are made out of these nanospheres. We can also build small nanorods, and that is used as a catalyst to crack and reform other materials. For example, we can convert crude oil into petrol. So one area that I was asked in the chat about is quantum computing, and quantum computing belongs to quantum technology. And we have a quantum research group here and even quantum technology center at our school. And there we do this quantum research. So what can you do with quantum research or quantum technology? One of the things is communication. So secure communication works like this. You can encode information into single quantum systems. Usually it's photons. That's like excitations, elementary excitations of electromagnetic waves. That means light. And these photons are so sensitive that if someone tries to eavesdrop and read out the information, he or she will change the state of the photons, and that can be detected. So as an example, we have, it was a proof of principle experiment, put such a quantum cryptographic device, that is this device with which you can send information that is secure against eavesdropping, and we put it into the stadium, into the Moses Mabhida Stadium, and connected it to the next police station, which is in the CBD. And then we encrypted all the information so that no one could read it out. It was a proof of principle experiment. And there was also some over actually I think a period of a few years where a line between Westville and Glenwood or so was used to do the to get some real world experience with these systems. Okay, so here you see a picture of satellites, and our university is involved in a BRICS collaboration, that is Brazil, Russia, India, and China, and of course South Africa. And we want to build a quantum network in South Africa that allows us to securely communicate in future. And maybe let me show you the next picture, which is here. You see this big metal cylinder, and it actually contains an atom trap. You can trap a few atoms in there. It's under ultra high vacuum, and these atoms can be used, for example, to measure time. So there are atomic clocks that don't win or lose a second in 30 billion years. Just to give you a feeling for that, the universe is 13.7 years old. So in the whole history of the universe, such a clock would not have gone 1 second wrong. And these clocks are very important for syncing and for GPS applications, so positioning applications. If you have satellites, basically every satellite by default, and every GPS satellite carries an atomic clock inside. Okay, so these are just examples of what you can do with quantum technology. Quantum technology is thought to be, one of the future technologies, and the South African government is at the moment has started a quantum technology initiative and tries to leapfrog this technology into industry. So my next example here is I have two more examples, and then I'm going to leave you, and they're both from chemistry. So this one is about batteries, namely usually, so if you have some cell phone or a computer, then you have good chances that you have a lithium ion battery, because lithium is a very light element. So the battery is very light, and you see here such a battery that is like comes in several layers with spacers in between. And basically how this works is you have some chemical compound, and the lithium is migrating from one chemical compound to another chemical compound, but leaves its electrons behind, right? That means this compound is then negatively charged, and where the lithium goes to is positively charged. And then if you put a wire between them, you have a voltage, a wire between them, you get electric current. This is the principle of a battery. And now if you want to recharge the battery, then you can do that by putting an external voltage and make the charges flow back, so that you get, and then the lithium ions also go back, and you can start the process again. But the problem is that you can damage this. You can damage the battery. For example, if you decharge it totally, then something might happen here. This is the normal structure of the chemical compound. Here you see the atoms, and they are in some kind of lattice, and here it's a little bit disordered. That is the damaged battery. And what we do is we use an electron microscope to actually investigate how can we make this more stable, and what does it mean that it's damaged, and can we recycle it, and so forth. And one of our ideas is to actually go away from lithium ion batteries, because lithium is a scarce resource, and it's also very dirty to mine, so it's not good for the environment, and go to sodium ion batteries. So here you see some sodium compounds. They come in different colors, and they could also be used for batteries. And sodium has the advantage that if you live at the sea, then you have lots of salt, and sodium is one of the components. Sodium chloride is salt. Okay, so that is not a scarce resource. Now, the last thing that I want to tell you today, and I would be happy if you are interested to come and visit us, then I can tell you much more. I can show you the labs. And so for us, I gave my address earlier on in the chat, and you can also find us on the internet, and then you can write us and we organize visits if you want, so that you can see it firsthand. What I want to tell you now, if you allow me, is about a special group. We have a peptide lab, and here in the cellar in Westville, and we have two of the world's most famous scientists in drug design working for us, and they are not only delivering or designing drugs, they often counsel companies, big companies like Pfizer. Here is this poster is from Pfizer. You know Pfizer maybe from the COVID vaccination drug. And this is a picture from Pfizer that shows how this all works. I mean, how a drug is developed. So usually it starts with some drug that you have already, like maybe it's a herbal, a chemical compound from some plant. And then you test that in the lab. Maybe, for example, you want to have something that kills microbes or bacteria, and then you have to first in the lab test whether it has the properties that you want. So this is what you do first, and then you have to check whether it's safe. So you go to some animals. Unfortunately, we have to do this. If you have a better, if you can find a better way, we would be very happy. And then it might go back to the drawing table and to the lab. It takes usually many rounds until we found what we need, and then it goes into clinical trials here and further up. And in the end, it is produced, but usually to produce a drug takes $800 million and 12 to 15 years. Now you can think of the COVID vaccine. It was produced in 1 year, which was fantastic. I mean, of course, a worldwide effort. Everybody tried to do this, and we can do it, but usually it takes much longer. And just to give you here a timeline, the drug discovery and preclinical phase is 3 to 6 years. Then there are the clinical trials, so where the drug is tested on human beings. And the first question is it safe? So that is the phase 1. You see here, we start maybe with 5 to 10,000 compounds. And after the preclinical phase, we have 250. Then we go down to, I don't know, in the end, it will be only 1 or 2 compounds that survive this process. So phase 1 is to ask, is it safe? The second phase is to ask, does it work? Third phase is it better than what we have now? Because we don't need new drugs if we have already drugs that are equally good. Okay, so these 3 phases is a total of 6 to 7 years, and then it has to be checked by some authority and be approved. For example, the FDA is the authority in America that approves drugs, and then only it can be produced. And producing is also not easy, right? And we have these 2 experts, and they teach our students to become experts in drug design, right? And this is, I mean, to study under people that are world-class scientists is really a privilege. So I can really recommend, if you're interested in something like this, then look at it and consider it. And if you want to hear more about modern future technologies, I can really say that we are very that we have a lot of application from our research, and that you can go into the corresponding industries. Please look at our homepage here for more information. And this is an old link here to the open day where you find a similar video, but we will put this video here on YouTube. Okay. So with these words, I want to just tell you that we have, of course, many other subjects. We do atmospheric physics, we do environmental chemistry, We do condensed matter physics. We do nanotechnology. Of course, we also do quantum computing, since you asked. And yeah, this is our program. It's really worth looking at it. I hope I made you some appetite, and I see you soon. Thank you very much. Back to Dr. Mashlambi. Thank you.
Thank you, Prof, for the valuable information regarding the research that can be done at UKZN. Okay, now I would like to give an opportunity to ask any live questions that you might have so that our speakers will help in answering them.
Just all you can do is raise your hand so we know who to go to. Any questions? I don't see any hands. Ah, there we go.
Yes.
Yes.
Please unmute yourself and go ahead.
Morning. I was wondering if one must apply online or if we must come to the university personally to apply, if we want to study at UKZN.
Okay. If you look at the School of Chemistry and Physics, the web page, under either one, if you click on chemistry or physics, there is a link there called registration, which will take you through the registration process, how to apply step by step. There's no walk-in. You are not allowed on campus. So you have to do it online, and we are still going via the CAO office. But the procedure is detailed online, how to go about doing it. And if UKZN is your first choice, you need to put that in as your first choice.
Thank you.
Okay.
Additionally, please note the closing dates for CAO application is the 30th of September.
Yes. In one of the college prospectus that is on the site as well, the date is given there. So please download. There's lots of downloadable PDFs on the site, so you can download it and go through it. I see somebody is still typing in the chat here. Do you guys offer astronomy for students who have not learned astronomy like a beginner?
Yes, so maybe I should answer this. Yes, so we have in our school, we have astrophysics, and in the School of Mathematics, there's also astronomy. And of course, you know, we always start you from the beginning, you know. So it is good to we already discussed it, to have a knowledge of mathematics from school. And but you can start with this if you have at least 30 points. And we heard mathematics is 5 points, but we encourage you to actually do better. It helps a lot if you come here with an A in math, you know. So but yes, the question to the answer is yes, we do this.
Okay, there's another question here that says, is the closing date the 30th of September for grade 11 learners to study in 2023? No, the current closing date of 30th of September is for those people who want to do, who want to start their studies next year. So it's 2022. For those who are in grade 12 and want to come to university next year, the closing date is the 30th of September. Okay, is there any other questions?
Okay, while we're waiting for questions, please also note that also the NSFAS application is also open for those who need funding, and it's closing on the 30th of November.
Yeah. You can find the funding information as well on the site. There's links to everything, to the access program, to the registration, to funding as well. Okay, there's another typed one here. During the explanation of the physics undergraduate program, certain elective options were highlighted as recommended over other options. Do they have a significant impact on the main modules that are studied? Okay, Dr. Dlamini, maybe you want to answer that.
Hi, sure. Well, the recommended electives sort of go well hand in hand with the main courses that you would study. So they are recommended because they sort of complement one another. You don't have to take the recommended electives because after all, it is an elective, but the reason that they are recommended over, say, other subjects is because we have found that they work well with our main courses. So if choosing electives instead of, say, choosing from all possible subjects, we try to narrow it down to the subjects that are going to complement your main major. And I don't know, maybe Prof. Conrad has got something to add on that.
Yeah, sure. So yeah, so the electives, I mean, of course it's important what you do as an elective. For example, if you want to study physics, then you know, we recommend in the first semester that you also study statistics and computer science, because math we anyway ask you to do. Let me just show you this. Maybe I can shortly share this. I think you showed the slide before. So basically here you see these recommendations in orange, okay, for the first and second semester. Math you do anyway, but you are also free. Someone asked, can I do marine biology together with chemistry? Yeah, you can, right? So of course there is a way to, you know, to do your thing, what you want, as long as you really do the courses that you have to do. You can choose in the electives. This is just our recommendations, and yeah. Sure, it helps a lot. So for example, here physics 231 is only an elective. It's the mathematical methods and machine learning, but it's very important to do it, I would say. All right. So please go through these lists and think about it, what you want to do. But of course, if you are individualist and you want to do something different, you are also welcome. Thank you.
The same, I can say that the same applies for chemistry, for applied chemistry. We do have a set of recommended electives, but again, that's up to you. If you want to do something else, you can. But we try to recommend certain things that will help you with your chemistry, like the stats and computer science and so on. So and maths as well. I'm not sure if somebody has their hand raised.
There are some more questions.
Yeah, there is another question there. Okay, so when one finishes grade 12 and other credits one can get, I don't understand the question. When applying, are grade 11 marks taken into account? Yes, you can use your grade 11. Well, obviously you haven't written your final exam yet, but you can submit your grade 11 if you have done your prelim or second term marks. You can send that, but you need to send in your final results as soon as you receive them. Or courses done in grade 11 in order to earn extra credits. Now, someone else also asked about they do extra courses. If your extra subjects at school are relevant to what you are choosing in your degree, then yes, they are considered. The points from those subjects are considered. Then if someone says who didn't do IT at school, can they still take that subject in university? Yes, that's what they actually prefer. They want a clean slate to write on. So they prefer you come with no knowledge, so they can teach you the right way. So yes, if you haven't done IT at school and you want to do it at university, yes, you can. But I think even there, I think the recommendation is maths. I think you need to have done maths.
Yeah, and 30 points, I think. Huh?
Yeah.
Or is it 28? Or I think 30.
So
for math, it's 30. No, it must be 30. Yeah.
Before one finishes grade 12, are there any other ways in which one can earn credits? No, we only take your senior certificate results. There's no other results that we take into account. So it's whatever exams you write from school, because it comes from an accredited body. So we use that. We don't take credits from anywhere else. Okay, I don't see. There's another one that comes in. No, nothing else. Is there anyone else? Okay, well, I think we've overshot our time by like 30 minutes, so we have to close up now. I just want to say that all our information is on the website. So if there's any questions that you still have and you want to post to us, our details, contact details are on the website, and you are free to send us an email and we will get the information and send it to you. I'll now hand back
Tishana,
yes.
There is one more question. Do we still have time? 1 minute?
Yeah, okay. Okay, it says what, one more or two more. What credits from AP courses? I don't understand that. It says, can you apply using grade 12 marks only? Do you have to produce grade 11 marks? It would be better if you send in your grade 11 marks. If you are worried that your grade 11 marks are not good, the reason why we say grade 11 marks is, remember, the university has a limited number of spaces. So you have to send in your application. So it's best that you apply early. Yes, you can also send in or come with your grade 12 marks once you do receive your results, but there is no guarantee that there will be spaces available. So there's another one here. Does the university accept pure maths and not maths literacy? No, maths literacy we do not accept. It has to be pure maths.
Can I say, it depends what you study. If you want to study science, you have to have pure maths. If you want to study literature, you can also have literacy, maths literacy.
Yeah, literature.
Literature and literacy.
So in science, it has to be pure maths and physics. So what date does grade 11 start applying? Okay, so if you're in grade 11 and you want to do something in 2023, then you would need to start looking at applications from July of next year. right? So July 2022, we start looking and putting your application.
Tishana, let me make a comment here. I'd love to invite the 11th grade pupils and their teachers to actually visit us. So if you are interested to see this firsthand, what we talked about now, then please
Yes.
come, right? Drop us an email.
An email.
You know, the best is, of course, if you can come with your whole class, try to convince your teacher. Maybe your teacher is here and is already convinced. Please come and have a look. That is always the best. You know, decisions should be made by actually looking at things and not so evidence. Science is
as we said, sorry, Prof. As we said, we have campuses here in Durban and in PMB. So if it's closer for your school to visit the PMB campus, you are more than welcome to visit the PMB campus as well. So
Tishana, can you help me with this AP courses? There's a question. Does the university consider credits from AP courses?
If you can define what is AP?
Yeah, you should know this probably. I'm not sure.
I don't understand.
Applied mathematics. Really?
Credits from applied mathematics or
chemistry. It's done as a subject at school. Look. Advanced program mathematics or physics. Fantastic. That sounds good. That's the advanced program, right?
That's fine. The other thing is when you're doing these advanced programs at school, you also need to tell us what was covered. So we can make an informed decision of how to apply the points. So we need to know what you did in these applied programs.
Okay, I think we have exhausted the list of questions for now.
Okay, thank you, everybody. We hand you back to Dr. Mashlambi.
Thank you. Bye-bye.
Okay, thank you, everybody, for attending. Hope you've got it what you have hoped to get when you join this session. Thank you to all our speakers for this valuable information. Then one more thing to take home for the attendees, please note that good work, it always pays. If you can get 6 distinctions from your matric, you will be able to get up to 25,000 scholarship from the University of KwaZulu-Natal. And then about 5 distinctions, up to 20,000. Please note this exclude the LO. Okay, so work hard. Okay, bye.
Okay, thank you, everybody. Have a good Saturday. Thanks.
Bye-bye. Bye-bye. See you soon, hopefully.